We are still in chapter 2, so we are still we are continuing with model diagnostics. So we're still looking at residual analysis. So if you remember last week, we discussed how to assess some of the assumptions that we made on the model using residual analysis. So we are going to continue from what we discussed last week. We're going to continue from there. So today we are going to look at two methods. The first one is the Debian-Western. So we're going to test for independence. Remember last week we used the graphical methods to check some of the errors or some of the assumptions that we made on the model. So we are continuing. We have two more tests to cover on this chapter. And the first one is the Debian-Western test for testing independence on the errors, because we assumed that the random error term or the errors are independent and normally distributed with a mean 0 and a constant variance. So we're going to test that assumption of independence. So if you read the first line, we are saying the standard regression inference assumes that the errors are independent, because if the errors are independent, it means the response variable is also independent. And because of that, the parameters or the estimators also follows a normal distribution. So when we have the estimator, which now we treat it as a variable, then we can standardize the estimator. Then that distribution or the distribution of the standardized variable follows a normal distribution with the mean and the variance. You saw, for example, with beta 1 hat. So if beta 1 hat is a variable and we standardize that, we end up with a z which is equal to beta 1 hat minus beta 1 divided by the standard deviation of beta 1, which is s beta 1. And that follows a normal distribution with a mean 0 and a variance 1, because beta 1 itself, or beta 1 hat, follows a normal distribution with mean beta 1 and variance sigma squared over SSXX. So it's because of that assumption that we are performing inference, or we are doing inference on these variables. So now we have the assumption of independence on the errors. We have an assumption of independence on the errors. So in situation where the data set is collected over time, the errors are likely to be serially correlated. So they are likely not to be independent in situations where the data set is collected over time. So where the data set is collected over time, the errors are likely not to be independent. So when the errors are not independent, then it affects the variances. It does not affect the estimate, the point estimate of the parameters, but it affects the variances of the estimate. And remember, when we are testing, we need those variances, because, for example, if we were to test if beta 1 is equal to 0 or not using a t-test or using an ANOVA table, we need the variance of beta 1. So if the errors are not independent, then now we have a problem, because we cannot trust the results, because of the errors or that independence thing will affect the standard deviation or the variance of the the response variable or the variance of the errors. So when we have a situation where the data set is collected over time, then we have to test if the errors are statistical independent or not, or if the errors are independent or not. And that test is conducted using the Deben-Weston or Deben-Weston test, which is one-sided. It's one-sided because in regression or in most of data sets in regression, the researchers discovered that the errors are positively correlated. So we test if the errors are positively correlated, because in most of the situations or in most of the cases that were solved before, the errors were found to be positively correlated. So because of that, we are having a one-sided test. We're testing if the errors are positively correlated or not. Is it clear? Is it clear?
Yes.
Thank you.
Yes.
So we are going to use the Deben-Weston test to check if the errors are positively correlated or not. So there you have the formula of the test statistic for Deben-Weston, which is DW. So DW is Deben-Weston, and the formula is the summation of T ranging from 2 to N of T of ET minus 1 all squared divided by SSE. If you look at what is there in the numerator or in the denominator, sorry, it's SSE. So it's the error of, or it's the error squared. It's the sum of the errors squared. So what we have in the denominator there is SSE. Is the sum of the errors squared. So that is the formula for the Deben-Weston, and this one is evaluated using the 4 steps procedure. Remember, I said even in the morning that every time when you want to test, you have to state the null and the alternative hypothesis. So the same thing here, we state what is our null and what is our alternative hypothesis. Then from there, we determine the acceptance or the rejection region, or the acceptance or the rejection of the tabulated value. So we go and read the value from the table. So Deben-Weston uses 2 values. We have the lower critical value and the upper critical value. So with Deben-Weston, we read 2 values from the table. We read the lower and the upper critical values. Then this is the formula for calculating the value of the test statistic. So this one is the formula for calculating the value of the test statistic, and here it's how to conclude. Yes.
Can you please go up for 2 seconds? I want to finish writing that formula.
No, don't worry. I will give you this notes immediately after this lecture.
Oh.
Yeah, immediately after this lecture, I will upload. If I forget, class rep, please remind me. So now we reject the null hypothesis. We reject the null hypothesis if DW, which is the value of the test statistic, is less than DL. DL is, this should be a small letter D. DL it's the lower critical value from here. I said we are going to read 2 values. So DL is the lower critical value. So if DW is less than DL, then we reject the hypothesis, the null hypothesis. And we fail to reject if DW is greater than DL. So we read the 2 values and we use both of them to conclude. If DW is less than DL, then we reject. But if DW is greater than DU, which is the upper critical value, then we fail to reject. And if our DW is in between the 2 values, or it's equal to the dw, it's equal to one of the two values, then the test is inconclusive. And then we have to go back and increase the sample size. Then we test again. Is it clear?
Yes. Okay, sir. So you
Yes,
said
sir.
this Deben-Wilson test, we use it to test for what?
To test if the errors are independent or not. Remember, if the errors are independent, it means the covariance of E1 and the covariance of E2 is equal to what? If the errors are independent and the covariance is 0, is there in chapter 1. So that's why here you see this formula of the correlation. So we're testing if they're correlated or not. Is it clear? Mema, you answered.
So, sir, since the
Yes, sir.
correlation can either be positive or negative, so in this case, we are just only testing for
Positive correlation.
positive correlation. Okay.
Yes, we're testing for positive correlation. And now I am concluding here to say ET and ET minus 1 are correlated if P is greater than 0. So they are positively correlated. They are positively correlated if we reject. If we reject the null hypothesis, it means we're going to conclude in favor of this one. So this will tell us that our errors are positively correlated or are correlated. Is it clear?
Yes.
Is it clear? Thank you. So the ET is the error that you know. Let me go to whiteboard. Let me go to whiteboard. So our model will look like this, which is YT, which is equal to beta 0 plus beta 1 XT plus ET. Because we are dealing with a time series data set. We are dealing with a time series data set, so we replace I by T. Simple to indicate that now we are dealing with time. So T1 and is the same as E1. We are just using T to indicate that now we are dealing with time. So don't be confused by ET. ET is the same as EI. Which is equal to YT minus YT hat. And we know that, again, I want to explain the part of ET minus 1. It's simply because, remember, ET or EI, let me erase this. The covariance of E1 is the same as the variance of E1. So we cannot check that, but we can check this. That's why when you look at that formula there, we have ET minus 1 is to avoid the situation where we are going to have ET minus ET. So to accommodate this, we take it as I mean, we take it as ET minus 1 squared. And this is nothing, by the way, is the covariance of ET minus 1. So if you expand this, it will take you to the covariance of ET minus 1. Is it clear?
It's clear, sir.
Thank you. Thank you. So now let's go back to the notes. Let's go back to the notes. So this is the null and the alternative. You will see how to get the value from the table, and this is the value of, I mean, is the formula, it's the test statistic formula, and this is how to conclude. Now we have our example. Now we have our example. We have the data set here. We want to check if the errors are statistically, or the errors are serially correlated or not, or are positively correlated or not. So we want to check that. We want to use the Ben-Weston test to check if the errors are serially correlated or not. So the first thing is to state the null and the alternative hypothesis. So the first thing that we need to do is to state the null and the alternative hypothesis. So the first thing that we need to do is to state the null and the alternative hypothesis. Then we get the value of the test statistic, which is DW. Yes?
Can I disturb you a little?
I'm listening.
I think I missed that point where you said, zero, P is less or equal to 0. I'm sorry about that. Can you please try to clarify me?
Which part are you referring to? This?
Yeah, it's network's giving me troubles.
This is the null and the alternative. This is the null and the alternative. So we are testing if the errors are positively correlated or not. So you know,
meaning if P is less or equal to 0. Continue,
if we fail to reject, this, there's a possibility that the errors are or P. It's not a P, it's a raw. This raw, this is the population correlation coefficient, by the way. So it's the population correlation coefficient. So it's the raw. So raw is equal to 0, or raw is less than 0. So those are the possibilities if we fail to reject this. So there is a possibility that the errors are not correlated. If this if we conclude like that, if the errors are not correlated, but if we conclude in favor of this, it means the errors are positively correlated. Is it clear?
Oh, thank you, sir. Thank you, sir.
Yes.
Is it possible to have a negative correlation?
Yes, it's possible. A correlation can be negative. Remember, when we measure the strength using R, that we are calculating a correlation. R can be negative, can be positive. But I said for the errors, we are only testing for positive correlation. We are not going to look at the situation where the errors are negatively correlated.
Okay.
Are you answered?
Yes.
Please, when you are answered, let me know so that I can proceed.
Thank you, sir.
So this is, thank you. This is the null and the alternative. This is the formula for the test statistic. And we have to calculate the value from to get the value from the table. So to get the value from the table, we need the sample size. and the level of significance. We need the sample size and the level of significance. So we go to the problem. Our sample size is 20, as you can see. It's the t is ranging from 1 to 20. So our sample size is 20. If the level of significance is not given, we always go with 5%. So in this case, we are not given, which means we are going for 5%. So now I'm going to project the table, the Ben Weston table, so that I can show you how to read the value from the table. Can you see the Ben Weston table?
Yeah.
Thank you. So we are not going to entertain the K part, which is the number of regressors, because ourselves, we only have one regressor. It's simple linear regression. So we are going to focus on this column where K is equal to 1. So when Mr. Malaga takes over, then you will look at the K is equal to 2, K is equal to 3, up to K is equal to whatever the number of parameters is going to or the number of regressors is going to have in the model. But for us, we are going to look at a situation where K is equal to 1. So as I've said, with the Ben Weston, we take two values, the lower and the upper. So as you can see here, for N it's equal to 15, for 5%, the lower limit is 1.08 and the upper limit is 1.36. So in our case, our N is equal to 20. So I'll go to N is equal to 20 and it's 5%, which means our lower limit it's 1.20 and our upper limit is 1.41. Is it clear?
Yes.
Yes, sir.
That's
Yes,
how
sir.
to read the value from the Ben Weston table. So our lower limit is 1.20 and then our upper limit is 1.41. So I'm going to write them on whiteboard. I'm going to write them on one. So our DL it's 1.20. Sorry, this is 20, and our DU it's equal to 1.41. So we need the value of the test statistic so that we can conclude. We need the value of the test statistic so that we can conclude. I'm going to use Excel to calculate. Remember, we need the errors. These are the errors. And for us to get the errors, it means we need to first get this. We need to first get this so that we can estimate YT1 hat, Y2 hat, Y3 hat. So we need to get the model first so that we can estimate this up to 20. Then from there, we calculate the error by using the formula YT minus YT hat. So we're going to first get the model, we find these values, then we find the errors. So I'm going to do this in Excel. I'm going to do this in Excel. So I'm going to project an Excel data set. So this is the data set that that I'm going to give you. That is in the notes. So now it's in Excel. I go to data, then data analysis. We feed the model. So we go to regression. We feed the model. So the Y range, we have the values and we have the X values. Now we can click here. We want the residuals. I can also feed the scatter plot on the residual plot. I can also feed this, but let me first feed the scatter plot. So if you look at the scatter plot, let me remove this. Now, How do we interpret this? How do we interpret this?
The annual sales, they are linearly, actually positively related to advertising expenditures.
Thank you very much. So you can see that there is a positive, and if you look at that, you can see that it's even perfect. All the points are on the line because I deleted the. Let me go back so that you can see. Orange represent the predicted sales. So you can see that when we have the predicted sale, you cannot even see the actual sales. So the thing is perfect. There is a perfect linear relationship. So you can see there's a perfect linear relationship. But we are not interested in that. We want the errors. So here are the errors. Here are the errors. So I'm going to take these errors. I'm going to take these errors and put them next to the values of x. So these are our errors. These are our errors. Or before the errors, let me also have the predicted values so that I can show you how we got the errors. So I will go back. These are the predicted values. These are the predicted values. These are the predicted y values because the actual values we have and the predicted y values are here. So I can take this, also include it here. So we also have this. And to get this column, this one of residual, I will just write EI here. It's simple. It's the actual value minus the predicted value. So we get minus 32.32 something, as you can see here. Then I can do that for all the values. So that's how to get the errors. So it's the actual value minus the predicted value. So we don't need this. We need only the residuals. So these are the EIs. Let me write it here so that you can see. This is ET. Now we are using T. We are not using I. So we are using subscript T. And here I'm going to have ET minus 1. ET minus 1 is nothing. This simply tells us that on this column, we are going to start from E2. I mean, the value for E1 will be at E2 because let me go back. Let me go back to the whiteboard and explain that part. Because if we have a column here, we have a column of errors. This is ET. And T is 1, 2, 3, 4. The second column, it's ET minus 1. Then here we're going to have E1, E2, E3, E4. It means here, when T is 1, here we're going to have E0. And we don't have 0 there because our T, our subscript T start from 1. So here we put a dash. Then when T is equal to 2, then we're going to have E2. When T is equal to 3, we'll have 3 minus 1, which is going to be, this will be 1. And here we'll have 2. Here we'll have 3, and so forth. Is it clear? Is it clear?
Yes.
Yes, sir.
So it means to get the values of this column, we are going to copy these values, but we paste them from 2 going down, which means the first value here, it's not going to be here, but on the second one. And the last value that was supposed to be here is not going to appear on this column. Is it clear? Is it clear?
Yes.
Thank you.
Yes, sir. It's clear.
Let me go back to this. So
Sir,
this means I can copy. For ET minus 1, I can copy this, and I don't take the last one. I copy this. But I paste from the second one because the first one should be left blank. So ET minus 1 for the first one, or for T it's equal to 1, then it's blank. I can even put a dash there, but I'm going to leave it like that. Then now, the second column, I want the difference of ET and ET minus 1. So I'm going to have the difference here, which is ET. Oh, sorry. I'm going to have the difference here, which is ET minus ET minus 1. So I'm going to have that difference there. And how do I get that? It's going to be ET minus ET minus 1. And I get that. So here we are going to have nothing because it's this minus nothing. But because I'm using Excel, I have to get that value. Is it clear?
Yes.
Sorry. So here we are not going to have anything. Now we are going to calculate from here. So for T it's equal to 2. For T it's equal to 2, we are going to have this value minus this one. Then we get the other values. We need to square these values. Remember, in the formula, this part is squared. So we have to square. I will first square the ET. So I will first square the ET. So we go to ET squared. We go to ET squared. So we're going to have this value squared. Or let me do it here. We're going to have ET squared. And that is the value. Then we also square this one. We also square this one.
Sir,
Yes, I'm listening.
what's that other column for? ET minus 1.
What is
That column of ET minus 1.
I don't understand your question.
The second last column.
Yes.
What is it for? Yeah,
It's
that
for
one.
ET minus, it's for ET minus ET minus 1. If you look at our formula for the test statistic, in the numerator, we have ET minus ET minus 1. So we are calculating the values for that column. You answered?
Yeah, thank you, sir.
Thank you. So now we need the totals. Remember, we have ET squared here. We need the total here because in the numerator, we need the total of ET squared. We need the sum of the ET squared. Even in the numerator, we need the sum of ET minus 1 squared. So we need these sums here. So I'm going to calculate the sums. I'm going to calculate these sums like this. So it's simple like that. Here are the sums. Here are the sums. So the sum for ET squared is this one. So I'm going to take it to whiteboard. I'm going to take it to whiteboard. It's 7587872. Let me go to whiteboard. So what we're getting from Excel is that the sum of ET squared, it's nothing but 75. Is it 8 what? 87872. Is it correct? Let's check. Yes, it's correct. It's correct. So it's 75878.872. And the sum of ET minus 1 squared, it's 8195 0.28. So if I go back to the board, I have, what is the value? 8195. So it's 8195. It's 8195.28. So it's the sum of ET minus 1 squared. And this is equal to what? I forgot that value. It's 8195.28. 8195.28. So this one is equal to 8195.28. So we have this now. We can go to the formula for calculating the value of the test statistic. So we can go to that formula, which is the DW formula. And the DW formula, where they are saying is T from 2 to 20 of ET minus 1 all squared divided by the summation. So when you sum this, what do you get? When you sum this, when we divide, when we divide these values, what do you get? When you divide these two values, what do you get? Come again. I cannot see what you are writing.
1.08.
1.08. Thank you. So this is our value for DW. This is our value for DW. So we have to check this with DL. Our DL, sorry, because we no longer need this, I can erase these values. We no longer need them. We no longer need these values. We no longer need those values. So now we have our DL, which is the lower limit. It was 1.20, and our DU, it was 1.4. Is it 41? Something like that. Let's go back and check. Yes, it was 1.41. It was 1.41, as you can see there. So now we have this. We have DW and these two values. And if we go back to the notes, we are saying if DW is less than DL, we reject the null hypothesis. So our DW, it's 1.08, and our DL, it's 1.2. So 1.08 is less than 1.2. Then what do? We reject the null hypothesis. We reject the null hypothesis. Where's the bot? Here it is. So our DW, which is equal to 1.08, it's less than our DL, which is equal to 1.20. Then we reject H0 and conclude that the errors are positively correlated. So ET and ET minus 1 are positively correlated. Is it clear?
Yes, sir.
Thank you very much. So that's how to test if the errors are correlated or not. That's how to test if the errors are correlated or not. If there's a question, feel free before we go to the next one. If there's a question, feel free before we go to the next one. So let's go back to the notes. Seems like there's no question. Now,
sir,
yes. I'm listening.
where do we get the 0.5? I mean 0.05.
When you test, you will always be provided with the level of significance. But in situation where you are not given, then you take 0.05.
You use the 0.5.
Yes. If you are not given the null, you take 0.05. Let me use this opportunity to clarify something, which I noticed last week Friday in the quiz. There are people who concluded, there was a question where I said construct an ANOVA table and use it to test at 5%. There are people there who concluded using MSR and MSE, or using the value of f being very far from 1. Remember, if f is close to 1, it means there's that relationship. It means the expected value of MSR is equal to the expected value of MSE. They are both equal to sigma. If you used that, I was marking you right. But if you did not include the level of significance, then I was checking something, because I gave you that level of significance for a reason. So I'm answering or helping those who used the f, comparing it to 1. If it's close to 1 or it's far from 1, then they concluded. So it was like that. But even if you used that, you should write the null and the alternative hypothesis. Because if you don't have the null and the alternative hypothesis, I'm also taking something. So you saw how the marks were allocated. Now let's go to lack of fit. Now we are going to lack of fit. We want to check if the model adequately fits the data. You noticed in one of the examples last week that we had a situation where we fitted a linear regression model, and the data set, the scatter plot was not linear. The scatter plot was not linear. So now we are going to test, not using the graph. We're going to have a formal test where we want to check if the model fits the data. We're going to check if the model fits the data. So we are still going with those assumptions that the errors are normally distributed with a mean of 0 and a constant variance. Remember, when we test, we need the variance and so forth. We need the distribution, and we can only get that when we have this assumption. So now we are not testing the assumptions like the previous tests, where we're testing the assumption we made on the errors. Now we are testing the function itself, or the model, if it fits the data. Is it clear? Because you are given a data set, you just decide that no, this one is for simple linear regression. But does that fit the data? Is that a good fit? Is that data for simple linear regression? So we want to test that using a lack of fit. But the lack of fit requires a repeat observations at one or more levels of X. So the lack of fit, this test requires that there should be a replication on the levels of X. So what it means is that, let me go to the whiteboard. What it means is that if we have our data set like this, if we have our data set like, let's say I, 1, 2, 3, 4, 5, then we have our Y1, our YI. So Y1 will be, let's say, is 10, 15, 20, 25, 30. There should be a replication here. So XI, let's say this is 2, and we have 4. Then we have 2 again. So that is the replication that we are talking about. So if you look at the values of X, for X1, we have 2, and y1 is equal to 10. Again, for x2, for x3, the value is 2, but the value of y is not the same as this one, because when x is equal to 2, when we substitute 2 from the model, remember our model is like this. The expected value of yi is beta 0 plus beta 1 xi. So if we substitute for x1 to be 2 here, if we replace here by 2 and we get 20, when you replace again by 2, you expect to get 20 because these values are constant. So what we're getting here is x1 is equal to 2 and our y is 10, but x3 is equal to 2 again, but our y is 20. So there is a replication on the x values. So lack of fit requires that we must have a data set like that, where there is a replication on the levels of x. Is it clear? Is it clear?
Yes, sir.
Thank you. Thank you. So the repeated trials for the same level are called replications. And the values, remember, let me go back to the whiteboard. Let me go back to whiteboard. So what we are saying there is that these are replications, and these are called replicates. So that's what we are saying in that statement. Now, how do we do this lack of fit thing? We decompose the error into two components. So in the ANOVA table that we constructed in chapter 1, we go to that ANOVA table. Remember, we have the SS reg, SSE, and SS total. So we go to that ANOVA table. We decompose the SSE into two components called the true error and the lack of fit error, or the true error component and the lack of fit component. So we are going to the ANOVA. So we are not starting from scratch. We are not starting from scratch. We need the SS reg, we need the SS error, we need the SS total. In fact, we need that ANOVA table from chapter 1. So we go to that ANOVA table and partition the error into two. So the first component, which is the true error, rests on the fact that the replicate on the fact that there are replications. So if there are no replications that in your data set, then you cannot have this, or you cannot use the lack of fit, as I have explained. So now we are going to do it like this. We are going to denote the number of levels. For example, let me go back to the whiteboard. We are going to donate the levels. Sorry. This is not what I'm looking for. Let me do this. Yes, I'm looking for this one. Let me write this, and let's say this one is 6 and this one is 4. So the x values, how many x values are we having here? If you look at this, how many x values are we having?
5.
Because we have 2 and 2, we have 4 and 4, then we have 6. So we are going to a situation where we're going to first put these values in order, so that in order, so that it can be easy for you to locate the replications. So for example, if we order this data set, let me create a space here. Let me create a space here. Let me create a space so that you can see what's happening. So we are going to do it like this. We are going to have xi xi, so we have 2, 2, 4, 4, 6. And the first value for x is equal to 2 is 10. Then we have 20, we have 15, we have 20, no, we have 80 and 25. So this is how our data set looks like when we order them or we write the values of x in order from the smallest to the largest. So you can see that now we have these replicates here or replications there. Now we are going to, I want to erase this if it's clear. Can I erase this?
Yes, sir.
Thank you. Thank you. So now we are going to write our data in this way. Guys, please, let's respect each other. You cannot just open the mic and start fleeting. We have x1, and the values for x1, our x1 is equal to 2. So our values for x1 there is I mean the y values for this, it's we had what? We had 10 and 20, something like that. And then we are going to have x2, which was 4, and we have x3, which was 6. So this is how we are going to have our data set, which means we have 3 levels. We have 3 levels of the regressor there. So let me go back to the notes. So if I go back to the notes, you will get from this statement that let us donate the different levels of x like this. We're going to donate the different levels of x like this. So we have x1, x2, x3 up to xc. So xc will be the number of levels that we are having. So in that example that I gave, it means we're having 3 levels. We're having 3 levels, x1 which is equal to 2, x2 which is equal to 4, and x3 which is equal to 6. And again, we donate the number of observations for the jth level as ni. So ni simply tells us, for example, n1, it means on the first level of x, we have how many observations? We have how many replicates? So in that example, we're having 2 because there were two replications or 2 replicates. The values of y associated with x is equal to 2. We had 2. And for x is equal to, or for the second level, which is x is equal to 4, we also had 2 replicates. But for the last one, we had 1. For x is equal to 6, which is the third level, we had 1 replicate, which means our n, if we were to use this formula, our n will be, let me go back to whiteboard. Our n will be, because here we had our n1, which was 2, even here our n2 was equal to 2, but here our n1 was 1. So we are saying the sample size is the summation of this, which means it was going to be 2 plus 2 plus 1, and we have 5. So that's what we mean by this statement, that the total number of observations is given by this. So it's the sum of the number of observations in the x levels. It's the sum of the number of observations in the x level. So the I represented the observation for the jth level. So if we have a situation like this, I want the whiteboard. If we have a situation like this, y1, 2, It means is the first observation on the second level. Remember, we had the levels x1, x2, x3, which means this belongs here, is the first observation for the second level. So y1, 3, for example, is the second observation, is the first observation for the third level. So it's going to come here. And y21, y21, it means is the second observation on the first level. And the second observation, let me erase this. And that second observation will come here, because here it will be y11. So this one must be the second one here. Is it clear? Is it clear?
Yeah, it's clear. It's clear, sir.
Yes, it's
Thank
clear,
you.
sir.
Thank you. Thank you very much. So that's what we are saying by this. That's what we are saying by that. Finally, we have the formula now. We have the formula, which is the summation of the observations per level. So we're going to find the sum of the deviations per levels. What's happening here? We're going to find the sum of the deviations per levels. Let me go back to the whiteboard. Let me go back to the whiteboard. Let me clean this and have x1, x2, x3. So here we had two values. It was 10 and 20. Here we had 15 and 30. Here we had only one value, which was 25. So this is I is equal to 1, I is equal to 2. This is the second observations on the first level. This one is the second observation on the second level, and here there's nothing. So it's like this. The nj's there represent the number of replicates. How many replications? How many replications are we having on the first level? Is 2. So n1 is 2, n2 is also 2, and n3 is equal to 1. So that formula that we are having there, which is the summation per of I from 1 to nj of, let me go back and check that formula. So it's yij minus y bar j. So it's yij minus y bar j. It's yij minus y bar j squared, which means if we're dealing with the first level, it means we're going to find the mean of this level. We're going to find the mean of this level, which is going to be y bar 1. So to get y bar 1, it's nothing but 10 plus 20 divided by 2, and that will give us 15. So the mean for this is 15. And to get this is going to be 10 minus 15 squared plus 20 minus 15 squared. And we get the answer. Here is going to be 5 squared. So it's 25 plus 25 is 30. So this one, for this column, we're going to have 30. We're going to have 30 here. We're going to have 30. We do the same with this. So this one is per column. So we're going to find of the deviations per column, or per x level. Then you will find those values there. And then when we have them, we sum them. So we're going, here we have 10, we're going to sum 10 with these two values. And that gives us our SSTB, which is the sum of squares to error. Let me go back to the notes. So the sum of squares to error, it's nothing but the sum of the sum. So it's the sum of the sum of the deviations per x level. Is it clear?
Yes.
Thank you very much. So the degrees of freedom for SSPE, the degrees of freedom for SSPE is nothing but n minus c. C is the number of X levels. So in our example, let me go back to the whiteboard. In our example, we have 3 levels. It means the degrees of freedom for this is going to be n minus 3. Our n is 5 minus 3. So our degrees of freedom was going to be 2. So that's how to get the degrees of freedom for sum of squares to error. And to find
Sir,
the yes.
can you repeat that part you wrote at the bottom?
Let me go back because I don't know which part are you referring to. Which one? This one?
Yes.
All right. I want to clean the board, so I want to first indicate that at the part that I'm going to explain. Please note these values because I don't know what's happening with me today. I forget these values. I don't know what's happening. So it's 10, 20, 15, 30, 25. So I'm cleaning that. I'm going to write our data set here. So X1 level, second level, and the third level. So we have I is equal to 1, I is equal to 2, because we only have 2 replicates on the first level, and it's 10 and 20. Now here we have is it 15 and what?
30.
And 30.
Yes.
And here we have 25.
25.
Now I will start with the NIC here. So N1, it's how many are we having? We're having 2. N2, how many observations are we having? We're having 2. How many observations are we having? We have 1. Now I also want to calculate the mean for this, which is Y bar 1. Y bar 1 here is going to be 15 because it's 10 plus. Remember, y bar is summation of yi minus or divided by n. So we only have two observations here. So we add them and divide by 2. So it's 15. We do the same here. We calculate y bar 2, and this is going to be 45 divided by 2. And 45 divided by 2, it's what? Is it 22.5? And we have only
Yes.
1, so the mean here will be that value because it's 25 divided by 1. We only have 1 value, so the value is 25 divided by 1. Now we want to calculate the deviations, the sum of the deviations. So the sum of the deviations for the first one, it's nothing but 10 minus their mean, which is 15 squared, plus 20 minus 15, 20 minus 15 also squared. So this is 5 squared plus 5 squared, and this will give us 50. Is it correct?
Yes, sir. It's
Is it
correct.
correct? Thank
Yes,
you.
sir.
Yes, sir.
So this it means
Sir.
this means we have SS1 here to be equal to 50. Now we want to calculate SS2, the sum of squares for the deviation for the second level. So we have the mean. And if we have the mean, it means to get that, we're going to have 15 minus the mean. Please press the calculator for me. Plus 30 minus the mean, which is 22.5 squared. And that total is the value for here. And what is that value? Please give me that value.
112.5.
112.5.
112.5.
Yes.
Thank you. And the last one, the mean is equal to the observed value. So the sum of the deviation is 0 here. This one is going to give us 0 because this mean is equal to the observed value. So this will give us will give us 0. Say, are you answered?
Yes, sir.
Yes. So that's what we are getting from this Let me go back to the note. That's what we're getting from this formula. But when we sum those SS1, SS2, and SS3, we get SSPE. So now when we go back to the notes and we have the sum of these, so it's SS1 plus SS2 plus SS3. This will give us SS2 error. Then what is our SS2 error? Is this these values, which is 162.5. Is it clear?
Yes.
Is it clear? Pohalo, what's happening? You are disturbing us, please. So that will give us the SSPE. That will give us the SSPE. And we are saying the degrees of freedom for SSPE is N minus C. And C is the number of X levels. So our degrees of freedom is going to be N minus C. Our N is 5 because it's the sum of this is 2 plus 2 plus 1 is 5. So our N is 5 and our C is equal to 3 because it's the number of X levels. We have 1, 2, 3. So we have N minus C, which is 5 minus 3, and that will give us 2, which means the MSPE is SSPE divided by the degrees of freedom. So now we have the MS2 error. We have the MS2 error. So when you divide this value by 2, you will get the MS2 error. You will get the MS2 error. So which is this? Which is that? So now that we have the SSPE, we know here that we have decomposed SSE into 2. Now we have one value. So if we have that value and we know what is our SSE, we can just go to our SSE and subtract that SSPE, and we'll get our SS leg of fit. We'll get our SS leg of fit. Is it clear?
Yes, sir.
Yes, sir.
Thank you. And the
Sir.
degrees of freedom,
Sir,
yes.
repeat
Yes,
what
I'm
you
listening.
were saying, sir. Repeat what you were saying about the leg. How do we get the leg of feet, sir?
SSLF, which is the SS leg of feet, plus the SSPE, which is the SS2 error. They are equal to the sum of the two, they are equal to SSE. So now that we have the SSE and we have also calculated SSPE, so we can get SSLF by subtracting SSPE from SSE. Are you answered?
I'm answered.
Thank you. So the degrees of freedom, it's C minus 2. So it's the levels of X minus 2. And then when we have that degrees of freedom, we can divide the SSLF by the degrees of freedom, and we get MSLF. And now when we divide the MSLF by MSPE, when we divide this by this, we get the F value, and we're going to use that F value to test for lack of fit. We're going to use that F value to test for lack of fit. So the F value for testing lack of fit is MSLF divided by MSPE. So from this ANOVA table, the SS reg is the SS reg that you know, the SSE is the SSE that you know, the SS total is the SS total that you know. Now we have these two parts which are coming from SSE. So we are partitioning or decomposing SSE into 2, and is the lack of fit and the 2 error. So when you sum these two, you must get SSE. And when you sum these two, you must get these degrees of freedom. And when you sum these two, you must get that. Is it clear?
Yes, sir.
Yes.
Thank
Sir.
you. Thank you very much. So we are going to do an example. Let me check our data set. We have this data set. Let me close this because we no longer need that. So let me do it like this. I'm going to, so that we can see the X levels. So that we can see the X levels, I'm going to do this, put this in order of the regressors. So from smallest to largest. So we have two levels, two replications on the first one, then two replications on the second one, two replications on the third one. Then we have one, which is 152. So we only have one, and the other ones are 2, 2, 2, 2, 2 like that. The other ones are 2, 2, 2 like that. So now I'm taking it to whiteboard. So I'm going to write this. So how many levels of X are we having? If I can ask that question. Here, how many levels of X are we having?
6.
So we have 6 X levels. We have 6 X levels. So I'm going to clean this. Now we have X1, X2, X3, X4, X5, X6. Then our X1 is 75. And we want the values of Y corresponding to 75 is 28 and 42. Is 28 and 42, which means we're going to have 28 and 42. So this is I is equal to 1, I is equal to 2. Then we go to the second level. It's 100. Our values is 112 and 130 and 136. So we have 112 and 136. So we have 112 and 136. Then we go to the third level, which is 125. We have 160 and 150. We have 160 and 150. So we have 150 and 160. We go to the fourth level, which is 75. We only have one, no, which is 150. We have only one value, which is 152. Is it correct? Yes,
Yes, sir.
it's correct. It's 152. It's 152. So here we only have one value, which is 152. Then we go to number 5, or the fifth one, which is 175. So we have 136 and 124. We have 136 and 124. We have 136 and 124. So here we have 126 and 134.
It
Then
is
we go
136,
to,
sir.
it's 136 and 124. Thank you. Then the last one is 124 and 104. So the last one is 104 and what? 120.
It is
What is that value?
124 and 104.
124. 124. Thank you. Thank you. So 120. 124. I don't know what's happening. Maybe because it's my last day with you, so I'm making these mistakes. This one is 124 and 136. So we have our data set like that. Now we can, our n1 is 2, n2,
Yes.
yes, is 2.
The
I'm
last
listening.
one, X6, you swapped the answers, the values.
No, the order does not matter.
Not sure.
Remember, the order does not matter. What you need there is the values. What you need is these values. Remember, we're going to calculate the deviations, whether you start with this or this. If this minus the mean is going to be 2, and this minus the mean is going to be 3, whether it's 3 plus 2 or 2 plus 3 does not matter. Are you answered?
Yes, sir.
Thank you. And N4, it's 1, N5 is 2, and N6 is 2. Now we can calculate the Y bar 1. What is Y bar 1? Please calculate those values for me. Y bar 2, and then Y bar 3. This one is simple. Y bar 4, it's 152. And then Y bar 5 and Y bar 6. Please give me these values. Please give me those values. And we need SS11 or SS1, SS2, SS3, SS4. This is 0. We need SS5, SS6. What is Y bar 1? You add these two and divide by 2.
It's 35, sir.
35. Then this one?
124.
124. Then this one?
124.
124. And then this one? Oh, the fifth one? 155. And then the last one?
Is 155.
Sir,
The last one?
No, sir, 150.
on Y3 is 155.
Y3, it's 155.
Yes.
155. 155. Then Y5?
Yes.
152.
This one is 15. No, Y5.
80.
Oh, Y5, 130.
It's 130. 130. Then the last one? The last one?
114.
114.
114. 114. Now, what is SS1? So it's simple. It's 113 or 113,5. Then SS2. SS2. It's 112 minus 124 squared plus 136 minus 124 squared. Then you sum the two. You give me the answer.
SS1 is equals to.
SS1 is there. Please, let's go to SS2. Unless that one is not correct.
28 minus.
I cannot see what you are writing. So please, if you have something, use the mic.
Plus.
SS1 is 98.
Is what?
98.
Which one is correct? Is it 98 or 113.5?
It's 98.
98.
Thank you. It's 98. Then the second one? Please mute your mic. Please mute your 288. Then the third one?
50.
250.
50.
50. Then the fifth one?
72.
72. And the last one?
132.
What? Come again?
It's 200.
200.
200. Thank you. So I can erase this because we don't need these values anymore. I can erase this. We don't need them anymore. Can erase this. Now we can get our SS2 error. Our SS2 error is the sum of these values. What do you get when you sum these values? It's 98 plus 288 plus 50 plus 0 plus 72 plus 200. And what is the answer?
908.
908. Someone is saying 708, someone is saying 908.
708.
Which one is correct? 708. Thank you.
708.
Thank you. So we have this. Now we need the SSE. So I'm going to run the SSE using the using this Excel so that we can save time, because time is not on our side. So you know how to calculate SSE because it's the same as the one from from chapter 1. So I'm going to run this. I'm going to run this. So I'm going to data. What's happening?
One.
My thing is not appearing here. Let me close this. Do not save. So we have our data set.
122.
Then we go to data, analysis of variance. Then we go to this regression. And then our Y value. Then our X values. No. Can be correct.
This is
what's happening?
gonna be.
We went from here. Yes, levels.
100 plus 100 is 200.
Now here's our ANOVA table. Please guys, mute your mic. Please mute your mic. So we have I'm going to delete this and leave only the ANOVA table. I'm going to delete this and leave only the ANOVA table. So I will delete these ones as well and leave the ANOVA table. Also. It's fine. So this is our ANOVA table, right? Where I'm going to insert two rows there. I want 2 rows. No, not. I want 2 rows. Guys, please mute your mic. Guys, please mute your mic. Marshall, please mute your mic. Prevents, please mute your mic. Thank you. Now, we are going to have lack of fit here. Lack of fit. We have lack of fit, and we have 2 error, as you can see there. So we have lack of fit and 2 error. And the degrees of freedom here. For this, we said is the number of X levels minus 2. So our X level there with 6. 6 minus 2 is 4. And we go to the next one. Our degrees of freedom for 2 error, it's n minus p, and our n there is 11, and our c it's 6. So we have 11 minus 6, it's 5. And you can see that 4 plus 5 is equal to 9 there. So that degrees of freedom it's fine, or those degrees of freedoms are fine because we have 2. Is it clear? Is it clear?
Yes, sir. Yes, sir.
Thank you. We have calculated the SS2 error. So the SS2 error, I'm going to take that value from here We calculated the SS2 error and he said it's 708. So it means here we're going to have 708. So 708 is the SS2 error. And the SS lack of fit is going to be the SS error minus SS2 error. So we're going to have 14,273.51 minus 708. And that will give us our SS lack of fit. Then we divide our SS lack of fit by the degrees of freedom, which is 4, and we get that value. We also divide our MS2 error by the degrees of freedom, which is 5, and we get the value. Now we need the F value. The F value is the MS lack of fit divided by the MS2 error, and that is our value. So our value is 23.95. Our value is 23.95. So we have to compare this value because this is the calculated value. We have to compare the calculated value, the F calculated value for testing lack of fit, and it's 23.95. 23.95. 23.95. We are going to compare it with the F tabulated with the degrees of freedom 4 and 5 at 5% level. And what is that? Let me open the T table. Quiz 1, where's quiz 1? There's an F table there. Here's quiz 1. Then we go to the F table to read 4 and 5. So 4 it's here, 5 it's somewhere here. So our answer is 5.19. Is it clear? Is it clear?
Yes, sir.
Yes, sir.
Thank you. Thank you. I want to go back to the board. So our answer, it's 5.19. But what were we testing? H0. E expected value of y is equal to beta 0 plus beta 1 xi, which means there's no lack of fit. And then we have not equal to beta 0 plus this, which means there is a lack of fit. So we're testing this and this. So you can see that the F calculated is greater than the F tabulated. And if this is the case, we reject H0. We reject H0 and conclude in favor of this, which means there is what? Because this one is telling us this is equal to this. So here there's no lack of fit, and here is saying there is a lack of fit. So we concluded that at 5% there is a lack of fit. Is it clear?
Yes, sir.
Yes, sir.
Thank you
Yes,
very
sir.
much. Thank you very much. So we are done with this chapter.
Sir, can you please
If you have
repeat
questions,
the conclusion?
come again.
May you please repeat the conclusion?
We reject because the calculated is greater than tabulated, and conclude that the expected value of y is not equal to that, which means there is a lack of fit. Because if the expected value of y is not equal to that part, something is not right. There is a lack of fit. Of course, at 5% level of significance.
Can you please repeat again, sir?
Ma'am, we are recording the session. We are saying, the first one we are saying, expected value is equal to this. So we are saying, let me change a color. We are saying expected value of y is equal to this, which means the model fits the data well. There's no lack of it. So the model fits the data well. So this one, we are saying expected value of y is not equal to this, which means the model does not fit the data well at 5% level of significance. So you can also write it like that. So the data does not fit the model well or adequately fit the model at 5% level of significance. Are you answered? Are you answered?
Yes.
RP.
Say Chay.
Are you still there? Guys, can you hear me?
Can you please upload the tutorial question after the lesson?